Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 2 for January 2022. I will do this paper in 3 parts. This is the first part, which is Section A, and I'll put the links to the other 2 videos, the Section B as well as Section C, in the description box below this video. Let's begin with question 1. Question 1 says, which are correct for the reaction shown? So here we have this reaction here, and as you can see, there is a carboxylic acid, let me use this, reacting with an alkali here, producing a carboxylic salt and water. The enthalpy change for the forward reaction is exothermic. So they say, which are correct for the reaction shown? The type of reaction, this is a neutralization reaction. The reason for that is the hydrogen from here and the OH from here interact to form water. And since 1 mole of water is formed, and there is a carboxylic salt formed. Remember, when metal hydroxides react with acids, we form a salt and water, and this reaction is going to be neutralization. So the enthalpy or the type of enthalpy change is neutralization, and the forward reaction is going to be exothermic. So the correct answer should be D for question 1. Question 2 says, which equation does not represent a standard enthalpy change of atomization? Now, standard enthalpy change of atomization is when 1 mole of gaseous atoms are formed from elements at standard conditions. In this case, we can see here we have formed 1 mole of gaseous atoms, correct, from its element. Magnesium as an element is in solid state, so that is correct. When we look at this one, oxygen as an element is in gaseous state, and here we see we have formed 1 atom of gaseous oxygen, so that is also correct. Mercury liquid, at room temperature or at standard conditions, mercury is going to be a liquid, and we can see we have formed 1 mole of gaseous atoms. The only problem is with this equation, we can see, yes, it's true, chlorine is going to be a gas, but here we have formed 2 moles of gaseous atoms, which is not representative of the standard enthalpy change of atomization. So here the answer, which is not representative, should be B. Let's move on to question 3. In question 3, they say, 5.2 grams of sodium hydrogen carbonate is added to an excess of acid. And again, you can see this is a metal hydrogen carbonate reacting with an acid. So they're going to say the temperature increases and the energy change is calculated to be 1030 joules. Now, this is the Q. In the equation, Q is equal to MC delta T. This is the Q that has been gained, so that has been calculated. So they say, what is the enthalpy change per mole of sodium hydrogen carbonate? Remember enthalpy change per mole. If we have Q, we know that delta H should be negative Q over N. The reason as to why this is negative is because this is a neutralization reaction. And again, an acid is reacting with a hydrogen carbonate, so water is going to be formed. So another thing I saw here is, since they've given us the mass of the hydrogen carbonate, we can be able to find the number of moles. So number of moles will be mass divided by the molar mass. The mass is 5.2. The molar mass is given here. You put it there and you get those moles. Since we know that delta H should be negative Q over number of moles, keeping in mind that this Q should be in kilojoules and not in joules, so we have to convert that to kilojoules. That is why you divide by 1,000 and you get negative 1.030 kilojoules. When you divide by the number of moles you get, you will get a negative 16.6397 and so on. But to round it off, it comes closer to negative 16.6 kilojoules per mole, and B is going to be the correct answer. The 2 equations I've used here is this one here and that. I used this to find the number of moles, and I've used this equation for enthalpy calculation. I fed in the information I had, and I was able to find the enthalpy change. Let's go to question 4. Question 4 says, the equation for the complete combustion of methanol is shown. So this is, we can see these are the reactants and those are the products. Here we can see that the forward reaction is exothermic since this is a negative value. So they say some bond enthalpy data are shown below. So here they're showing us all the bond enthalpies, keeping in mind that this is a carbon-oxygen double bond only in carbon dioxide, not in methanol. This is for that, not that. So they ask, what is the carbon-oxygen double bond enthalpy of methanol? So what we are trying to find is this. So remember the equation, delta H of any reaction, if you have bond enthalpy, should be the sum of the bonds broken minus sum of the bonds formed. So here I had to find the summation of the bonds formed individually and then the summation of the bonds broken. So I began with the summation of the bonds formed. We know we have formed 2 carbon-oxygen double bonds and 2 oxygen-hydrogen bonds. So here I know 2 carbon-oxygen double bonds and 2 oxygen-hydrogen. So multiply 2 by the enthalpy of each of that when I multiply by 2, and then 2 times this one here. When I sum these two, I get that. So this is the total enthalpy of the bonds formed in the product side. Now I had to look at the reactant side. At the reactant side, we see we have that, we have 2 of these, and we have that. So that for this oxygen broken, and these 2, so you get 2 times that, but this is what we're looking for. So I put them here. We can see we are looking for that, but we have each for carbon hydrogen multiplied by 2. You get, and then that. When I sum this and that, I get 1324, which is 1,324. Remember, I am looking for this one. So I fed this and that into my equation, keeping in mind that the enthalpy change was already given to be negative 591. So negative 591 should equal to the sum of the bonds broken minus the sum of the bonds formed. Remember, the sum of the bonds formed was already calculated. So if I keep this the subject, that goes to the other side and that goes to the other side. And finally, I get 623 kilojoules per mole as my answer. And you can see this is going to be A. Moving on to question 5. Question 5, the first part says, which sequence shows the molecules in order of increasing boiling temperature? Now we have to look very clearly. If you're talking about increasing boiling temperature and these are all simple molecules, we have to know the intermolecular forces of attraction involved. In this case, we can see water. Water is going to have a higher boiling point in comparison to all of this. So this one here, methane, cannot have the highest, that is out. And here we can see chlorine cannot have higher than bromine because, as you know, bromine is below chlorine in group 7, so it has more electrons, so this is also out based on that. When we come to this, we can see bromine and water. Water should be the highest because it has intermolecular hydrogen bonds, while the others only have London forces. So I also try to calculate the number of electrons here. They are 10. Try to make this one 17 times 2, and that 35 times 2. And we can see, in comparison to London forces, these 3 bromine should have the highest, so this order makes sense. And since each water molecule can form 4 different intermolecular hydrogen bonds, this is going to have the highest boiling temperature. So the answer ends up being D. Moving down here, which is not correct about ice. Ice has a lower density than water. That is correct. It floats on water. Water molecules are farther apart in ice than in water. Of course, that's correct. Water molecules in ice are held together by hydrogen bonds. That is correct. The only difference is the hydrogen-oxygen-hydrogen bond angle is the same as in water. That is wrong, so the answer here should be a C. Question 7 says, which intermolecular forces exist between the molecules of the compound shown? Now we can see here, we're going to have a lone pair there, and of course here we're going to have 2 lone pairs, and here 2 lone pairs on that. So we have permanent dipoles because there is a carbon-oxygen, and there is an oxygen-hydrogen, so we can have we're going to have a permanent dipoles. We are also going to have London forces, and since we have OH, we can have intermolecular hydrogen bonds. So here the answer ends up being D. So let's move on to question 8. Question 8, this question is about alkanes. Which of these alkanes has the highest boiling temperature? So since these are all alkanes, it means they only have London forces between them, and the highest boiling temperature is going to exist in the alkane with the longest chain. And again, remember, these are all straight chains, so the longest chain is going to be the one that has the highest boiling point because it will have more London forces within it. Propane has 3 carbons, this one has 5 carbons, that one has 6, and that one has 4. So the one with 6 has the greatest number of carbons or the greatest London forces within it, so it should have the highest boiling temperature. Part B says, which of these alkanes has the lowest boiling temperature? Since all these alkanes actually have 7 carbons, it means they have the same number of electrons within them. So the difference is going to be due to branching. And as you already know, branching reduces the points of contact for formation of London forces. So the most branched alkane is going to have fewer points of contact, and therefore it will have the fewest London forces formed. So here the answer should be A, because it's the most branched, so it will have the lowest boiling temperature. Question 9 says, which solvent dissolves the greatest amount of hydrocarbon? The hydrocarbon, as you can see, is just an alkane. It doesn't have any intermolecular hydrogen bonds or any permanent dipoles, so it only has London forces. Therefore, it should dissolve in the most nonpolar solvent. When we look at butanol, we see it's an alcohol, so it has OH. Therefore, it has ability to form intermolecular hydrogen bonds, so it is not the most nonpolar. Ethanoic acid can form permanent dipoles, London forces, as well as intermolecular hydrogen bonds, so it is not the most nonpolar. When we go to water, of course, everybody knows water is a polar solvent. So here the most nonpolar is going to be hexane because it only forms London forces. So it will make perfect interaction with this alkane here. Therefore, our answer for question 9 should be a C. Let's continue to question 10. Question 10 says, which reagents would convert the alcohol into an alkene? And again, remember here, to convert an alcohol, let me give you an example. An alcohol like ethanol, if you are to convert it to ethene, it means we need to eliminate water. And the only thing that is very good at eliminating water in this case should be phosphoric acid. That is used as a catalyst in this reaction. So concentrated phosphoric acid, this answer here should be C, as you can see. The next question says, which name is correct for the ion in this one, in sulfate? So we are looking for the ion in sulfate. Now we know this is sulfate, but we need to find the oxidation state of sulfur. Assume the oxidation state of sulfur is X, and we know each oxygen here is -2. So -2 times 4 gives us a -8. The overall is going to equal to -2, which is the charge on the ion. So when I take 8 the other side, X becomes a +6. So this should be sulfate 6, because in this ion, sulfur has an oxidation state 6. So here C becomes the answer, sulfate 6. Oxidation state of sulfur is +6. Question 12 says, in which compound is the oxidation number of nitrogen +5? Again, you have to use the same method that I used up here, like that, if you want to calculate the oxidation states. But when I did that, I found out that this nitrogen here was 5, the nitrogen here was -3, the nitrogen here was +3, and the nitrogen here was +3. So A is the only compound that gave me a +5 oxidation state for nitrogen. Question 13 says, in which reaction is copper species acting as an oxidizing agent? One thing we need to know is an oxidizing agent gets reduced in a reaction. So we need to look at the reactant side and the product side and look how copper has been changed. Here we can see it's going to be 2+ and it's changed to 0. That is a reduction. +1, in this state it's still +1, so there is no change that has occurred on that copper. Here we can see 0 becoming copper 1 as well as copper 2, so there is oxidation. And then we can see copper 0 becoming copper 2, that is oxidation. So the only place where it's acting as an oxidizing agent, meaning it gets reduced, is in A. So A should be the answer for question 13. Moving on to question 14. Question 14 says, two half equations for a reaction are shown below. So we have half equation that and half equation that. Imagine, let me first delete what I wrote so that I can show you. That is how these equations work. So this half equation and that half equation, and then they ask us what is the overall ionic equation for this reaction. Before we can write an overall equation, we have to make sure the electrons in both reactions are exactly the same, because the one that gets oxidized produces electrons that are going to be used in by the one that gets reduced. So in this case, it means we have to multiply this equation and that equation appropriately to create the same number of electrons. Since these are 2 and these are 3, we have to multiply this whole equation by 3, and we have to multiply this equation by 2 to create 6 electrons here and 6 electrons here, like I did already. So that is why I did. So I say times 3 here, and then I say times 2 here. When I did that, we can now create similar electrons so the reaction can proceed. Now, since we have similar electrons, to balance this up, so this is going to be 3 copper. Look for anywhere you have 3 copper. It's only here. When I multiply this by 2, it's going to be 2 nitrate. And then that is times 2. It gives me an 8. This one times 2 on the other side should be NO2, and that's going to be a 4, while the other is going to be a 3. And then that's it. So basically C should be the answer. If I combine these two equations after I'm applying them appropriately, I'm going to get C as the correct answer. Question 15 says, a titer of 13.25 centimeters cubed was obtained using 50 centimeters cubed burette. What is the percentage uncertainty in the titer? They said each reading of the burette has an uncertainty of this. Remember, you read a burette twice. So in the beginning and again at the end. So you multiply the uncertainty times the number of times you read the burette, divide by the value you have measured times 100. And when I did that, I got a plus or minus 0.75%, which is B. If we go to question 16, they say barium hydroxide reacts with sulfuric acid as shown below. So this is the equation of how they react. They ask which is the ionic equation for the reaction. The ionic equation, when we are writing an ionic equation, we'll break apart the aqueous only. So breaking this aqueous, I get that and that. When I break that, I get that and that. But on the other side, we can say this is a solid, I cannot break it, and that is a liquid, I cannot break it. So this ends up being my overall ionic equation, and you can see it's only existent in A. The others are not. So there is nothing that cancelled out here because on the product side, there is nothing that was aqueous. Let's continue to question 17. Question 17, here they say 4 tests used to identify ions are shown. So there is a flame test, there is addition of acidified barium nitrate solution, addition of acidified silver nitrate solution, addition of sodium hydroxide solution, then testing any gas with indicator paper. They say which test could be used to positively identify the ions in ammonium chloride. So what I wrote here is I said for ammonium, what we usually do is you use sodium hydroxide, you add sodium hydroxide, and then you warm. When you warm, a gas is going to come off. This gas is ammonia gas, and that gas turns damp red litmus paper blue. So for this case, we will use sodium hydroxide, and then we can use litmus paper. So this test here makes sense for the identification of ammonium cation. Chloride side, we use a nitric acid followed by silver nitrate. So when we look is acidified silver nitrate. So we can see test 3 and test 4 can be used to identify the ions in ammonium chloride. So our answer here should be a D. Now question 18 says, which conditions give the highest yield for the forward reaction? Now remember, highest yield for the forward reaction, we have to look at it's producing more products. Which conditions are going to produce more products? The conditions we are looking at are temperature as well as pressure. Since the forward reaction is endothermic, it means it's going to be favored by an increase in temperature. So a higher temperature will shift equilibrium to the right-hand side, producing more product and creating a higher yield. So I said higher temperature shifts equilibrium to the endothermic side, which is the product side. So we need high temperature. And for pressure, we need lower pressure because when you lower the pressure, equilibrium is going to shift to the side that has more moles of gas. So since this side has more moles of gas, we need to lower the pressure so that equilibrium shifts to the right-hand side. So when we see it's only B that has higher temperature, lower pressure, so it's the answer for question 18. Let's continue to question 19. Question 19 says, nitrogen dioxide and dinitrogen tetroxide exist in equilibrium. This is the equilibrium. We know that nitrogen dioxide is brown and the dinitrogen tetroxide is going to be colorless. So they ask, when an equilibrium is set up in a gas syringe, the mixture is pale brown. When the mixture is compressed, the color becomes... Now, because it's going to be pale brown, when you compress the syringe, you bring more NO2s closer. Since, remember, the brown color is due to the NO2s. So if it's going to be pale brown, compressing initially brings a lot of these NO2s that are brown in color together. So the mixture is going to turn darker initially before they continue to react. However, due to compression is leading to increase in temperature. Now, since the product side has fewer moles of gas, when you increase the pressure, it means equilibrium is going to shift onto the other side. So again, one more time, initially you compress, you bring more of these that are brown colored together, creating a darker appearance. However, as you bring them together, the pressure has been increased, so equilibrium shifts to the side that has fewer moles of gas, and that's why we're going to produce a colorless gas, which is dinitrogen tetroxide, and in this case, the mixture is going to turn lighter. So the answer here should be C. It turns darker and then lighter. The explanation is all written here. I said equilibrium shifts to the side with fewer gaseous moles, so it will turn darker. The reason for that, because the molecules are compacted. NO2s that are brown in color are going to be compacted initially, then it will turn darker. And then it will be lighter because equilibrium will be shifted to the product side, producing the colorless gas. So the answer for question 19 is going to be a C. This brings us to the end of section A and the end to this part. Please do not forget to subscribe. I'll see you in our next video, and please remember I'll put the links to the 2 other videos in the description box of this video. See you next time. Bye-bye.